Okay, hi everyone. So we've been working with approximating the area underneath the curve. So the big deal is that we're approximating. Because as we've been seeing before, when I draw that curve, and I try to fill this curve, we'll call this like 4 or something, right? And 0, which we're trying to fill this curve with boxes. And of course these boxes don't get close enough to our curve. And in some cases we're overestimating, in some cases we're underestimating. Now how do we get better approximations? Well, of course, this n, let's say, was 1, 2, 3, 4, 5, 6. This n was 6, meaning I have 6 boxes here. But if I make n 10, the same curve, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, excuse 1, is going to be closer. So we end up with less gaps, right? So on and so forth. And I mean, if you guys are into graphics and if you're trying to buy that 3070 card, 3080 card, 3060 card, I guess, from NVIDIA, like the idea is more pixels, more detail. The curve is nicer. And in the real world, in a digital world, we actually cannot form that nice curve. It's all about pixels. It's all about approximating. So we're going to get into integration when we can find the actual area underneath the curve. And we're going to do an example of that today. But we're also going to introduce a slightly better shape than a rectangle. Okay, someone might say, "Mr. Go, a triangle." Well, if I draw this curve for you, and we say triangle, can I really fit a triangle in this shape? Right? Like how would you fit triangles?
Lots of empty space.
A lot of empty random space. So triangles is not the answer.
Unless you put them
Is it a
upside down
trapezoid?
after.
And Jacob called it is a trapezoid. Maybe Andrew, you were gonna say triangle on top, I think, right? And
No, I meant like upside down. See how there's like that space that forms another
yes,
triangle?
then that is actually the shape of a trapezoid. So let me go ahead and draw
Yeah.
the shape of a trapezoid. And a trapezoid is actually, you can think of it as also two triangles-ish, right? And actually, that's the area of a trapezoid. It's actually the area of two separate triangles. And so that's our shape today. We're going to solve this using trapezoids. And trapezoids kind of get a lot closer to our curve. Okay, it gets closer to our curve. And it's a better way of approximating, though it's more work, right? Nothing's easier than a rectangle. But trapezoids will give us a better approximation. But of course, if you want more detail, it's always going to cost us more work, just like anything else.
So why are we approximating when we could just find the integral?
You're right. Because before us being able to find the integral, this is what they had to do. And actually, us building an approximation will lead us up to actually finding the integral. Okay. And the big deal is here, for instance, in my first example, n was 6. And you can see there's a lot of gaps. N was 10. Gaps are a little bit better. If n was 100, the gaps would be even smaller. And not until we hit n of infinity, okay, would we actually be on the curve. But who wants to do an infinitely many set of rectangles? No one does.
Yeah.
So this allows us to see a couple of things, and we'll get to that. And the integral, though, we say f of x dx. It's really a basic idea of base times height, where f of x is your y value, it's your height. And dx is that little bit of base. Now, how wide do you want the base? You want the base to be so small that it's practically nothing. And the way you can think of it is you're going to go b minus a divided by infinity, which is 0. Okay? Where b and a are our starting ending values of our definite integral. Okay. So let's go ahead and talk about trapezoids today. Let's talk about the area of a trapezoid. Area of a trapezoid is 1/2 base, 1/2 height, b1 plus b2. Now, let's look at the shape of a regular trapezoid when we look at it. So we have a base 1, a base 2, a height. Right? That's usually what we look at a trapezoid. When I spin this around for what we're going to use, spin this around, and we're going to stand this straight up. This was the height. This was base 1 and base 2, right? And just a flashback to geometry. Why do we have this crazy equation? Is because if I just draw this again in a slightly different way, one triangle, oops, I drew it wrong. Oh, not really wrong, but this is actually two triangles, base 1, base
Mr. Cole,
height. Yep.
what is it on the side next to the top trapezoid? Like that? That's just the arrow, right?
Yeah, I just drew a little loop-de-loop. Yeah,
Alright.
a little loop here. It's not a real mathematical symbol here. Okay, just a loop-de-loop. Because I'm just turning it on the side. Is that if you look at the area of this one triangle, this triangle is 1/2 base times height. The second triangle here is 1/2 base times height, area of a triangle. And if we add them together, 1/2 base 1 height plus 1/2 base 2 height. Take a look, they both have a 1/2, don't they? So 1/2, and they both have a height, b1 plus b2. That is the equation from geometry for the area of a trapezoid. It's really just two triangles, which is kind of cool. Okay, so I'm going to give you a really super easy version here. We're going to look at a problem. And we're going to look at the problem as y is equal to x squared plus, let's say plus 4 to give us a little bit of space. And we're going to find the approximation between 0 and 2. Okay, the approximation between 0 and 2. So if I plug in 0, that's going to be 1, 2, 3, 4. Put a dot. At 1, it's going to be 5. And at 2, it's going to be 8. 1, 2, 3. 1, 2, 3, 4. And we're going to approximate this area underneath the curve. In this case, it's going to be an over approximation. And we'll talk about a little bit about that y later. So I'm just going to draw this so you guys can see it nicely. Two lines. In red. Okay, over approximation. And over approximation. Okay, hopefully you guys can see the trapezoids being formed. So in this case, please see that it is an over approximation because it's curved going up. And now we'll notice something in a little bit. I'll talk about concavity. How do you know if it's going to be an over approximation or under approximation when it comes to the trapezoid rule? And it's going to be referring to concavity. But you can see this is is better than if I just drew rectangles. Again, let me draw a left side approximation here. I'm going to erase it, but you guys can take a look. Left side, and left side. This is what the approximation would look like if I just chose a left side approximation. And you would agree that the trapezoid more contours, you could say, to the curve of the shape. What if I do a right side approximation? Do right side? Here we go, right side. And that is a major over approximation, isn't it? See how all that extra goodness I take? So I want you guys to see that the trapezoid definitely is a better model. Okay. All right. So a couple numbers we want to write. So cool thing is that the steps aren't really hard. You just have to know what the y values are. So the y value here is 0, 5, and 8. You guys feel good about that? 0, 5, and 8? What is the base of each of these rectangles or these trapezoids? The base is 1 and 1, right? In this case. So we actually have everything we need for our trapezoids. So for the first trapezoid is 1/2 base, 1/2 height, which is 1, and then b1 plus b2. That is the area for my first trapezoid. I'm sorry, what?
Why is it 0, 5, and 8? Why not 4, 5, and 8?
4, 5, and 8. So, oh yeah, you're right. I'm sorry. This was 4. Thank you for catching it. I just thought of a 0. You're right. It's 4. You're right. 100%. Thank you for catching that. This is 4 and 5, right? Okay. For my second trapezoid, we repeat the equation. 1/2 base, which is 1 here. And then we're going to look at 5 and 8. Okay.
Wait, so why do you multiply by 1?
Okay, so look back here. The area of a trapezoid is 1/2 height B1, B2. Okay, so we're doing 1/2 height. The height here is tilted. We mentioned before we're going to tilt our height over. That's really our quote-unquote new base. And that, in this case, in this example here, was 1.
Alright.
Cool. And then we're going to go ahead and just, the rest is just an approximation. The area approximation is 4 plus 5 is 9, so 1/2 9 is 9 over 2. I'm just writing 9 over 2. 5 plus 8 is 13, plus 13 over 2. And we're going to add this together. We end up with 22 over 2, which is 11. Right, so that's an approximation. If we did the left rectangular LRAM, this would have been 4 times 1 is 4. 5 times 1 is 5. We would have had an under approximation. So if we did LRAM, let me erase that just so you guys can see that. So this is our trapezoid area for, I'm going to do a little trap here, was 11. If we did the area with LRAM, this would have been 4 and 5, right? 4 plus 5 is 9. If we did our area approximation with RRAM, our right area approximation, that would have been 5 and 8. You guys cool with 5 and 8? Because the base is just 1. That's why it's kind of easy for us to talk about so quickly. So 5 plus 8 is 13. And I'm not going to do the midpoint because I would actually do more work for that. Okay. Now, the follow-up question is, now that we kind of know how to do integration, what would have been the actual area? So let's do the integral. Integral between 0 and 2 of the function x squared plus 4 dx. Okay, so let's go ahead and take the integral of this. X cubed over 3 plus the integral of 4 would have been 4x. I want you guys to double check this real quick. If you're not good at it yet, go ahead and double check. If I do the power rule of 3, 3 comes down, cancels this out, becomes a 2. We're back here. All right, let me do this one more time just so you guys can see what I'm doing in my brain. If I bring down the 3 cancels out with that 3. And then the 3 becomes a 2. That's our x squared. Just double check. And we take the derivative of 4x, that's just 4. Okay, just double checking my work in case I make a simple mistake. And then I'm going to draw my bar between 0 and 2. We're going to plug in our 2 and 0. We're going to end up with 2 cubed over 3 plus 4 times 2 minus 0 cubed over 3 plus 4 times 0. In this case, I don't have to write the 0, but I'm just writing it so you guys can see that I actually use both numbers. Of course, 0 cubed and 4 times 0 isn't going to matter to us. We're going to end up with 8 over 3 plus 8. I'm going to rewrite that 8. Actually, no, we don't have to. We can just combine this to become, this is 2 and 2/3 plus 8. You guys okay? 2 and 2/3. And this adds up to become 10 and 2/3. Now, this is the exact value. So today's homework, I actually had some questions where you are going to graph it and find the actual value in addition to the approximation. So you guys can see the differences, okay, and how close we are. Now let's take a look. If our actual answer is, and if we're asked to write units, this would be units squared. If you're asked to answer units, okay, just FYI if you were ever asked to answer units. Now, our trapezoid approximation was pretty darn close. Now, I want to bring up a couple of cool things also. Looking up here, isn't the trapezoid approximation for concave up an over approximation? See how we're a little over the graph? And our answer is a little bit over our 10 2/3, which kind of lines into exactly what we're doing. We know that 9 was an under approximation. We know 13 was an over approximation. So all this stuff makes physical sense, which I think is very cool. Okay, now the trapezoid approximation is going to be better, but you can see it took us a lot more work. All right, we were able to do left and right in literal seconds versus like the minute and a half it took us to do the trapezoid. Okay, so more accuracy takes us more work, and that's everything in life. More accuracy, more work. If you want me to draw a detailed portrait of myself, you know, that's me, right? That took me 2 seconds. If you want me to do more work, you can add nose, add some glasses, add balding hair, right? More work, more detail. Oh, Mr. Ko, that looks just like you. Okay? Yeah, sad. So that's what the thing about mathematicians have to do, and in business. If you want high detail, you have to do more work. But is it worth your time to do more work, right? And that's always something that we're kind of weighing. All right, let's do another problem here. Let's do, well, I think that's pretty self-explanatory how to do trapezoid method. Okay, let's do 2 more real quick since we're at it. Let's do inscribed versus circumscribed. Okay, so these are 2 more approximations, inscribed and circumscribed. So we can then let me just give you a quick graph, and then you'll kind of see what I'm talking about. Here is a graph of one. Here's a graph of another. See my idea? Sorry, I need to let someone in. Oh, she's here. Okay, so I'm going to break this into 4. 1, 2, 3, 4. I'm going to try and match that over here. 1, 2, 3, and 4. Okay, so what is circumscribed and what is inscribed? Here's the thing. I forget which is which till I realize one of them has the freaking word in it. Okay, in means all your rectangles must be inside your graph. Okay, circle means I guess you gotta go circular around it, and we use all our extra ones. Okay, so if you take a look here, this is inscribed. So all my rectangles are inside the shape. And all are, for circumscribed, all are on the outside.
So pretty much one's just a little under and one's a little over the exact amount?
Yes, and that's the goal of this actually. I want to overestimate or I want to underestimate. If I'm cheap, I'm always going to underestimate, right? But if I want to make sure everyone has enough to eat, I'm overestimating. So these are both different tools. Now, how do we make sure that your answer and my answer are the same? The big deal is that we both understand if I'm doing circumscribed, we are always going to choose values that are over. So you're over and I'm over. So we're not mixing them both. And that's the thing about these methods. These methods are here to communicate the method I'm using. And if I'm using this method and you want to get the same number as my method, we're both going to use the same technique. It's not just a random approximation. If I do left and you do left, we always get the same answer. If you do right, I do right, we'll get the same answer. If I do inscribed and you do circumscribed, of course they're different. And they're labeled as such. Right? So that's the big deal. Now, the cool thing is that if I do say inscribed, I know this is going to be a under approximation. If I do a circumscribed, I know that for sure this is going to be over approximation. Right? So if you're, for instance, the right-handed media, right? So right skewed media, you'd be like, oh, inscribed, the coronavirus is not that bad. But if you're super left, you're like, you would use circumscribed numbers. Oh, the virus is raging and everyone's dying, right? So it's all about how you want to use this information. So it's kind of cool. If I want to overcatch or undercatch. And again, these are approximations. This is before the actual idea that we can find the actual value using an integral. Okay. Now, if we're doing modeling, depending on the purpose, if we're trying to over or underestimate, we would use inscribed or circumscribed, which is kind of cool. These are just different tools that we want to all agree to. Today in IXL, that's what you're going to do. You're just going to find rectangles, inscribed or circumscribed, and the rectangles are actually drawn out for you for the most part for most of these questions. So you can see the differences between them all. Now again, are these hard ideas? Not really. These are really just geometry ideas. Okay. Let's see. Let's do another example. Let's give ourselves one more example. Let's come up with, let's do, find the area, approximate area, using one, we'll use trapezoids, and 2, we'll use inscribed, and 3, we'll use circumscribed. For the function f of x is equal to, we'll do x plus 2 and x minus 4, and we'll do between 1 and 4, and we'll say n value is going to be 3. Okay, so this is really x squared minus 2x minus 8, and we're going to graph it between the values of 1 and 4, and we're going to break it into 3 different rectangles. Okay. So here's a couple things. You could graph it, and I can graph it, but you know what? Let me just draw you the x value real quick. 0, 1, 2, 3, 4. All right? We could spend all our time in the world graphing it, but I'm not going to. I'm just going to plug in the values. If I plug in 1, what does the graph look like at 1? Plug in 1, 1, or just plug in, I'd rather plug in 1 here in the factor version. 1 plus 3, 1 plus 2 is 3, and 1 minus 4 is negative 3. Wait, did I make a mistake here? The positive 4 should have been 0. Oh yeah, whoops. I'm going to throw a negative in front, folks. Negative in front. Do me a favor, do a negative. Negative in front here, I'm going to flip the signs. Negative in front, flip the signs. Make my life easier. I was drawing a concave up when I really meant it to be concave down. Okay, so that's where I messed up. Okay, so I'm going to stick a negative in front, and we take a look, negative in front, and I also flip my function around. Okay. So if I plug in a 1, this would have been 3. It would be 3. If I plug in a 1 here, that would be negative 3. It becomes a positive 9, so we're going to be 9 up here. So I'm just going to write 9. I'm not going to even draw it. It's 9. If I plug in a 2, 2 plus 2 is 4. 2 minus 4 is negative 2. So negative 2 and 4 is going to be negative 8. Becomes a positive 8. Next value is 8. Plug in 3. 3 plus 1 is 5. 3 minus 1 is negative 1. So that's going to be negative 5, so positive 5. And 4, if I plug in 4, 4 minus 4 is 0. So what I want to show you here is I'm not spending my time graphing it. I'm just writing the numbers because all we need are the numbers. Okay, let's go with our trapezoid. Looking at my first shape here, that's going to be area for trapezoid. So 1, trapezoid, right? So that's 1/2. The height is 1. Nice and easy 1. That's my height here is going to be 1, right? And my 2 bases are 9 and 8. Okay, no graph needed. All I needed was the y value. Plus 1/2, 1. Oh, the next trapezoid, see, is my next trapezoid 8 and 5? Right? You could draw it if you want, but don't waste your time. That's going to be 8 plus 5. Or you could save time and just say 13. If you want to just say 13 and 17, you could save a lot of time writing. And 5, last one is 5 and 0 plus 1/2, 1 of 5 and 0. And that would have just been 5, right? So 17 over 2 plus 13 over 2 plus 5 over 2. By our powers combined, we end up with 18, 20, 35 over 2. And that's our approximation. All right. So what if we decide to do inscribe? Now, if you look at these numbers here, inscribe, I'm just going to draw the curve, like some very easy version of the curve. Inscribe means all our values would be inside. But here's the other way of looking at it. It's all the smaller numbers. If you want to be inside the graph, you want to be smaller than the graph. So given a choice of 9 or 8, you would choose 8 because you want to be inside the graph. Given a choice of 8 or 5, you want to choose 5 because you want to be inside the graph. And here's a tough one that people always get stuck on. How about 5 and 0? Well, just like our rules before, which one's smaller, 5 or 0? We would actually use 0 here. So to do our inscribed, it would have been 9. Nope, not 9 because we want to be inside, right? So we would have chose 8 height times base times 1. Choose between 8 and 5 for my next rectangle. I would have chosen a smaller number. I would have chosen 5. Between 5 and 0, I would have chosen the smaller number. I would have chosen 0. So our inscribed value is going to be 13. Now, given our trapezoid value was going to be 17.5, yeah, inscribed is a lot smaller. And we knew this was going to be an underestimate. Underestimation. Okay, we knew it was going to be underestimation. Let's go ahead and look at 3, our circumscribed value. So remember, circumscribed is over. I want to make sure I over cover. All right, I'm double checking here. So between 9 and 8, I would have, of course, chosen 9. That would give me an over coverage. Between 8 and 5, I would have chosen the 8. And between 5 and 0, I would have chosen the 5. So again, this would be 9 and 1. This would be 8 and 1. And given a choice between 5 and 0, I would have chosen 5 and 1. And this is going to be 18, which is for sure an overestimation versus 17.5. Okay, now let's actually do the actual value. So if my function here, if f of x, when we multiplied it out, we originally said this was going to be x, negative x plus 2, and x minus 4. Now, just like derivatives, you don't want to take the derivative of this. I don't. So we're going to multiply this out like we did. It'll be negative x squared plus 2x plus 8. So this is our function. And we're going to take the integral of our polynomial. It's always super easy to take integrals of polynomials. It's just a power rule. Us dealing with factor form, nope, ain't doing that. Isn't helpful. So we take the integral between, we said 1 and 4 of negative x squared plus 2x plus 8. And we have to write a little bit dx. Now again, to remind you what this formula means, this is our f of x. This is our y value. And dx is a little bit of base. This is our base. Very, very small. A very, very little bit of base. And base times height gives you that rectangle. And the integral gives us an infinitely many set of rectangles. So here we go. Now, what does this symbol here, this integrand symbol means? It's s, because this is the idea of sum. I'm going to add up all the parts. So here we go. Let's just go ahead and follow our power rule. X cubed over 3, 2x squared over 2, plus 8x between 1 and 4. You can simplify this by dividing the 2 in the x squared. Make sure you write the equal sign. Now, after I take the integral, we do not write dx, right? Dx is gone, okay? Dx is gone. And now go ahead and plug in the values and see if you guys can do this by yourself. We're going to remember plug in the 4 minus the 1. If you want to save time, I'm going to go ahead and write, just plug it in as squaring it. I'm going to write parentheses. I always write a parentheses for the negative one because I always forget to distribute that negative sign. Okay, so make sure you do have that negative sign. It's a very common mistake. Um, (32/2) is just 8. On the right side, we're going to end up with plus 1/3 minus 1 minus 8. You could also just combine those to become 9, right? Save yourself some time. Save yourself some time, let's call that 40, right? So negative 64/3. We're going to say this is plus 40, right? And this is minus 9. Combine those together, it becomes 31. Plus 1/3 plus 31. Oh, wait, what? Oh, yeah, wait, we're not done yet. Okay, and I'm just going to subtract this over. Becomes negative 63/3. And that becomes 21. Negative 21 plus 31 is, wait, did I make mistakes someplace? 21.
Can you divide out the 2 for the 2x²/2?
Yeah, you can cancel that out.
So wouldn't it
Oh, it
just
should have been 16, yeah. I was wondering where I messed up. The number didn't make sense. Let me fix that. Thank you for catching that. 16, that would have been 48. Right, 48 minus 9 is 39. There you go. I was wondering why my numbers were too small. And the answer is 18. Okay, so 18 is the actual value, the area underneath this curve between 1 and 3, no, 1 and 4. We said our approximate was trapezoid was 17.5, which is darn close. We knew we had an underestimation of 13 and overestimation of 18. Now this overestimation of 18, it turned out to be the same number here, right? It turned out to be the same number, but it wasn't done the same way because we did overestimate, right? And looking at the graph, like this overestimation should have been a lot over, but I think what happened is probably this corner here. Okay. Did I do the math right? It's 18?
Isn't it 22?
Oh, dang it. Did I subtract it again wrong? Oh my gosh.
No, not on this part, in the circumscribed part.
Oh, did I? You're probably right. This plus this. Oh, that was a 5. Whoops, I added the 1. Oh my gosh. Mr. Ko. I'm too lazy to edit that out of the video. Why'd you tell me now? Sorry. It's like a mother blaming their kids. It's because I said 1 plus 9. That's what I did in my head, which it should have been 5 plus 9. Thank you for saying it's 22. Bunch of pigeons. All right, but thank you. So now it makes total sense. I was like, what? It should have been way over because when we overshoot, there is no under. I was like, I'll try and fudge it. Okay, so we're actual. All right, that's it.